Welcome back to the second lecture on an introduction to graph theory and networks. Today we'll be continuing on in the handout that was linked either down below or on the page where you found this video, starting with page 6. So today we'll start with this problem. Suppose we're given a map, such as this one below, and we want to know the minimal number of colors required to color the map so that no two bordering countries are the same color. So let's look at this map here. We can try to use graph theory to solve this problem. So the first thing we would want to do is try to represent this map as a graph. Remember, a graph is a set of vertices and edges. Those vertices we can think of as objects, and the edges we want to think of as connections between those objects. So thinking about a map, what are the objects, and in what ways are those objects connected to each other? Especially when we want to think about coloring these countries so that no two bordering countries are the same color. In this case, they're states. So I would think of the states as objects. So I would represent the states as vertices or points. You can draw those in here. And then the connections that are important for this question would be that two states are connected to each other, or those two vertices are connected by an edge if they border each other. So we want to draw an edge between two vertices if those states border each other on the map. Okay, and we get this graph, which we can recreate to the side here. Okay, there are all of our states, and we draw on the edges. Okay, so now that we have a graphical representation of this map, we want to think about what kind of things we want to impose on this graph to answer the question. So now coloring countries or states on our map is now the same as coloring the vertices of our graph. So how can we translate the requirement that no two bordering countries or states are the same color as a requirement on the coloring of the vertices? Well, if states or countries are bordering each other on a map, that means there's an edge connecting those two vertices. And remember from yesterday, if two vertices are connected by a single edge, we say those vertices are adjacent. So this requirement is that no two adjacent vertices are the same color. So that brings us to the idea of a coloring of a graph. So we say a coloring of a graph G is an assignment of a color to each vertex so that no two adjacent vertices are the same color. And a K coloring of G is a coloring that uses exactly K colors. So let's look at this example. We have these two graphs here, and we want to decide whether these are colorings of the graphs. So why don't you pause and think about that for a minute. Now that you're back, let's talk about whether these are colorings of the graphs. So in this first graph, we want to assign a color to each vertex, and we don't want any two adjacent vertices to be the same color. So here we can see that if two vertices are connected by a single edge, those two vertices are a different color. So this is a coloring of the graph. And then on this graph over here, these two vertices are connected by an edge. They're adjacent, but they're both the same color. They're both red. So this is not a coloring of the graph. Okay, another thing we can do is, given a graph, we can give an example of a coloring of that graph. So let's give an example of a 3 coloring of the following graph. So what we want is to assign a color to each vertex so that no two adjacent vertices are the same color, and we use 3 colors to do that. So why don't you pause the video and try that on your own. Okay, so now that you're back, let's talk about an answer. So I'll let my 3 colors be red, green, and blue. If you have markers or something, you can color them in. I'll just write R, G, and B for the colors. So I think what I'll do is start with this vertex that's in the middle here, connected to so many other vertices. I'll just call this one red, R. Okay, so now that any time a vertex is adjacent to this vertex, we want it to be a color that's not red. So we can go to this vertex that's adjacent, can label it green. And if we go here, this vertex is adjacent to both the green vertex and the red vertex. So we need to label it blue, a different color. Okay, moving down to this vertex, it's adjacent to both blue and red, so it needs to be green. Again, we only want 3 colors here, so we don't want to introduce a new color. All right, this one's adjacent to green and red, so it needs to be blue. This one's adjacent to red and blue, so it needs to be green. And this vertex is adjacent to green, green, and red, so we need to make it blue. Once we've done that, there's only one option for this vertex. It has to be red. And then we can choose any color we want for this vertex here. So let's just say it's green. This next vertex can be either red or blue. Let's just make it red. And then this last vertex can be green or blue. We'll make it blue. Okay, so we've labeled all of our vertices with colors. No 2 adjacent vertices are the same color, and we've used 3 in total. So this is a 3 coloring of the graph. Now let's look at this next example. Is there a 2 coloring of this graph? If so, give an example. In other words, color or label the vertices. And if not, explain why. So why don't you pause and try to think about this one. Now that you're back, let's talk about it. So you want to go off of instinct here. If you think there's a 2 coloring, you'd want to try to draw one in. If you think there's not, you have to figure out why, instead of just saying, I couldn't do it. So what is the problem with this graph here? Or what are the potential problems? Well, I go straight to this part of the graph, this triangle. Notice that in a triangle, all 3 vertices are adjacent to each other. So there can't be a 2 coloring of this graph because we need 3 colors to color in this triangle. So no, there's not a 2 coloring. So since there is a triangle in the graph, all 3 of those vertices are adjacent. So we need 3 colors to color in the vertices. Therefore, there's no 2 coloring. Okay, so now what is the smallest number k such that there exists a k coloring of the graph we just looked at here? So in order to figure this out, we need to find a coloring and say that there's no smaller coloring. So since we just said why there's no 2 coloring, the next thing you would want to look for is a 3 coloring. So why don't you pause the video and try to do a 3 coloring of this graph. If you can't do that, try for a 4 coloring and try to think maybe why you can't do a 3 coloring, etc. Okay, so now that you're back, there is a 3 coloring of this graph, and we can write one down. There are a lot of them. We start by labeling this green, then this one can be, this red, then this one can be green, this vertex can be red again, this one can be green. All right, then we can label this vertex green, we can label this one red, green, and each of these can be red because they're not adjacent to each other. They're only adjacent to that green vertex. And this vertex can be green. So far, there is a 2 coloring of this graph, and then the problem lies right here. So if we label this vertex red, we can call this one green, and then this has to be a different color because it's adjacent to both a red vertex and a green vertex, so we can label it blue. So there does exist a 3 coloring, and as we explained earlier, there's no 2 coloring, so the smallest number k such that there exists a k coloring of this graph is 3. So k equals 3. So this is what we call the chromatic number of a graph. The chromatic number of a graph G is the smallest number k such that there exists a k coloring of G. And we write this as chi of G. So let's do an example. Let's find chi of G for this graph here. So we're looking for the smallest number such that we can find a k coloring of the graph. So pause the video and try that on your own. Okay, so now that you're back, let's see what chi of G is. We can start by trying to color in this graph. It'll help us think about things. So if we call this vertex R, then we can label this one green, and we have to label this new vertex blue because it's adjacent to both red and green. So far what this tells us, since there's a triangle, that chi of G is at least 3. It's possible we'll need even a 4th color. So now we can label this vertex red or green, doesn't matter. So we can label this one green. Okay, and here's another triangle. So this vertex here can't be red or green. It's adjacent to both of those. So we'll label it blue. Okay, but now there's a problem with this vertex. It's adjacent to a red, green, and a blue vertex. So we're going to need a 4th color. Then we can continue on. This one's blue, so this can be red, green, or yellow. And this vertex, let's just label it green, and we'll label this one blue. Okay, so chi of G is 4 here, and let's explain exactly why that's true. Okay, so the chromatic number, must be at least 3, since there is a triangle. And in fact, it must be, since I'm running out of room, it must be at least 4, since there are 4 vertices in the middle there that are all adjacent to each other. And then we found, where should I write this? Write it up here. We found a 4 coloring. So this means the chromatic number is 4. Right? So now let's interpret our map coloring problem in terms of the definitions we just learned. So what are we trying to do? We're trying to color in our map so that no 2 bordering states are the same color. So we drew it as a graph here, and we wanted no 2 adjacent vertices to be the same color. And we wanted to know the minimal number of colors required to color this map. So what we're looking for is the chromatic number of G, the chromatic number of our graph. So it turns out that every map can be colored with 4 or fewer colors, and this is what's called the 4-color theorem. So the 4-color theorem says that every map can be colored with 4 or fewer colors. In other words, the chromatic number, chi of G, is less than or equal to 4 for any graph G that comes from a map. And these are called planar graphs. And you do have to be a little careful because there are actually some exceptions. We don't want countries or states to be split up. So we want them to be connected, and it needs to be a graph or a map on a sheet of paper. So this theorem was actually proven in 1976, but the proof was done by checking thousands of special cases on a computer. So to mathematicians, this is very unsatisfying. Technically it's proven, but no human could ever actually read through the entire proof. That's how long it is. So we would like to see a more elegant proof, and it would be really cool if one of you could come up with that. Okay, so let's talk about something called bipartite graph. So we say a graph is bipartite if it has a two coloring. So let's look at this graph here. Why don't you pause and decide if the following graph is bipartite and say why or why not. Okay, welcome back. So it's bipartite if it has a two coloring. So if we can find a two coloring, we know it's bipartite. So you can label this vertex red. Okay, then all of these adjacent vertices down here have to be labeled with a new color. We'll do green. Okay, and then any vertex adjacent to these green vertices has to not be green, and notice that none of these vertices are adjacent to this first red vertex, so we can label all of them as red. And this gives us a two coloring. So an equivalent definition of a bipartite graph is if the vertices can be put into two distinct sets where none of the vertices in the same set are adjacent. And you can see by the picture of the graph, or the way that the graph is drawn here, all the vertices on the top are not adjacent to any of the others on the top, and none of the vertices on the bottom are adjacent to any of the vertices on the bottom. So these are the two distinct sets that we're talking about, the vertices that are all given the same color in a two coloring. Okay, so are these two graphs bipartite? Why don't you pause and try to figure it out? Okay, let's talk about it. If they're bipartite, we can find a two coloring. So let's label this vertex red, and this one has to be green. This one can be red again. This one's green. Okay, and now we've run into a problem because this vertex is adjacent to both of these, but this vertex is red and this one is green, so this has to be blue. So there's no two coloring. So it's not bipartite. This one, however, we can find a two coloring. We just do red, green, red, green. There's no problem here because this last vertex is adjacent to the first one, and they're both different colors. So here's a two coloring, and this graph is bipartite. Okay, so graphs that look like this are what we call cycles. A cycle in a graph is a path. So remember, that was a walk or a set of distinct edges that we can draw without picking up our pencil. And since it's a path, the vertices are all distinct. We don't visit any vertex more than twice, except if it's the vertex we're starting and ending with. So a cycle in a graph is a path that starts and ends at the same vertex. So they look like these closed loops here. So let's suppose we have a cycle in a graph G of length n. And what that means is there are n edges in the cycle. So here in this first graph, we have 5 edges. So this is a cycle of length 5. And in this graph here, we have 4 edges. So this is a cycle of length 4. So what's the relationship between the number of vertices and the number of edges in a cycle? You can draw some examples to see what's true. So after you've paused and thought about that, we can see in these examples here, this cycle that has length 5, it has 5 vertices. This cycle of length 4, it has 4 vertices. And so for a cycle of length n, it will have n vertices. You can see that because we can identify each edge with the vertex it starts with. Okay, we do that for each edge in the cycle, and then when we get to the last edge, we identify this edge with the vertex it starts with and the vertex it ends with is the starting vertex of the next edge. So there's what we call a bijection between the edges and the vertices. So there we have the same number of them. So in a cycle, the number of vertices is equal to the number of edges. And a cycle can have even or odd length. So what do you think is true about the relationship between the length of a cycle and whether or not that cycle is bipartite? Maybe think about the examples we did above. So why don't you pause and think about that for a minute? Okay, so if you're coming back, let's maybe think about these examples here. So this first cycle had odd length, and it was not bipartite. The second cycle had even length, and it was bipartite. Okay, and in general, that's going to be true. So a cycle is bipartite if and only if it has even length. So why does this make sense? Well, you can think about a coloring of the vertices in a cycle as just listing out an alternating sequence of red and green. Oops. So we make it alternating. Okay, it'll continue on. And this will be a two coloring of the graph if and only if the last letter or color that we write down is different from the first one. And that will happen if and only if this has even length, the sequence of colors we're writing down. And it's the same as the number of vertices. So that tells us the cycle is bipartite if and only if it has even length. So this also means that the following theorem is true. A graph G is bipartite if and only if it does not contain a cycle of odd length. So if we have a graph and inside that graph we have a cycle of odd length, that means that that cycle alone cannot be colored with just two colors. So the whole graph can't be colored with two colors. So let's do this example, an application. Let's suppose Alicia, Bob, Chelsea, Diego, Edward, and Fred were hired for an internship. The company wants to split them into two teams for a team building activity so that no person knows any other person on their team. Suppose Alicia, it's supposed to be Alice, knows Bob, Chelsea, and Diego. Edward knows Bob and Chelsea, and Fred knows Alice and Diego, or Alicia and Diego. So is this possible to do? Is it possible to split them into two teams where no person knows any other person on the team? And we want to prove our answer. And the number of people on each team doesn't matter for this question. So why don't you pause and try to think about this for a few minutes. If you come up with what you think is your answer, try to prove it. So now that you're back, hopefully you've tried to use graph theory to answer this question. So we want to think about how we can get a graph from the information we're given here. Again, a graph is a set of objects and connections. Those are the vertices and edges in the graph. So what are the obvious objects here? Well, I would say the objects are the people, and the connections between them are that two people are connected or two vertices are adjacent if those people know each other. So we can start with the first piece of information we're given. Call this vertex Alicia or Alice. Supposed to be the same person. So Alice knows Bob, Chelsea, and Diego. So we can draw an edge between those vertices. Then Edward, we can draw another vertex here, knows Bob and Chelsea. Okay, and Fred, label that vertex with an F, knows Alice, draw an edge over here, and Diego. Okay, so in terms of this graph, what question are we really asking here? We want to know if we can split these vertices into two groups where no two vertices are adjacent. So no two people know each other in that group or on that team. Well, remember what we said from earlier, how an equivalent definition of a bipartite graph is that the vertices can be put into two distinct sets where none of the vertices in the same set are adjacent. So that's what we're looking for here. We want to know if this graph is bipartite. So this graph looks really close to that first bipartite graph we saw. But what's different? Well, look, we have a triangle here. The vertices A, D, and F are all adjacent to each other. Okay, what that means is there's no two coloring in this graph, which means it's not bipartite. So there's no way to split the vertices into two groups where none are adjacent. The answer to this question is no. It is not possible because our graph is not bipartite, and that's because it contains a triangle. So I'm sure there are other ways of answering that question too, but you can do it using graph theory. So the last topic we'll get to today is complete graphs. We say a graph is complete if every pair of vertices in the graph G is adjacent. So there's an edge between any two vertices. And we denote the complete graph on n vertices by k sub n. So I want you to pause this video and draw K1 through K5 and see which ones you can draw so that no edges intersect except at vertices. So why don't you pause and try that now? Okay, now that you're back, let's draw all of these. So we'll start with K1. That's the connected graph on one vertex. So we just draw one vertex, okay, and there are no pairs of vertices, so we don't draw in any edges. It's just a single vertex. Let's draw K2. This is the connected graph on two vertices. So we can draw in our two vertices, and we want them to be connected by an edge. So that's K2. Then for K3, drawing our three vertices, and each pair needs to be adjacent, so that will look like a triangle. Next is K4. We're able to draw this so that none of the edges intersect. So we'll have our four vertices. You can start by drawing a square. That's planar, meaning none of the edges are intersecting. Okay, we can connect these two vertices here. And my first instinct, at least, is to connect these two, crossing over this one, but we don't want them to intersect, so we can draw them going around. Also, there's no problem with drawing the complete graph so that the edges are intersecting, but it's just a fun exercise to see which ones are planar. We'll end with K5. Is this one planar? So drawing our 5 vertices. You can start by drawing a pentagon to connect these outer ones in, remember this is a cycle, length 5. Then we can start connecting the inner vertices. So that's the most we can do on the inside without edges intersecting. We need to connect these two, and we need to connect these two, and we need to connect these two. So we can go around like this, and we can go around like this. But now we still have to connect this vertex and this vertex, and it's not possible to do without intersecting edges. So this one's non-planar. So that's K1 through K5, and you can have the complete graph for any value n. That's a positive integer. Okay, so now we have some questions about complete graphs. I want you to try to answer these on your own first. So the questions are, first, is K3 bipartite? And then, is K4 three-colorable? So does it have a 3 coloring? Can we color it with 3 colors? And then try to think about, is Kn n-1 colorable? Okay, so now that you're back, let's talk about it. So is K3 bipartite? Well, it's bipartite if it has a 2 coloring. You could try to draw and see that you can't do one. And why is that? No, it's not bipartite because all 3 vertices are adjacent to the others. So we need 3 colors. Is K4 3-colorable? And no, for the same reason. All 4 vertices are adjacent to the others. And is Kn n-1 colorable? No, for the same reason. All n vertices are adjacent to the others. So then is Kn n-colorable? Well, yeah, we can just use n colors. We can color each of the vertices a different color. Then we're not in danger of having any 2 adjacent vertices be the same. And can a graph G be n-1 colorable if it contains a copy of Kn? So think about this for a minute. And the answer is no. If it contains a copy of the complete graph on n vertices, we need n colors to color that section of our graph. So we need at least n colors to color G. We might need more than n, it depends on what else is in our graph. So we get to our last example for the day. Is the following graph 3-colorable? And prove your answer. So why don't you pause and think about that for a minute. Okay, so now that you're back, let's talk about it. So you want to go first off of your instinct for this one. If you think maybe you can color this using 3 colors, you should go ahead and try that first. Maybe you did. And if you can't do it, we'll have to think of an argument or a proof for why it's not possible, instead of just saying, I couldn't do it. Because just because you can't do it doesn't mean it's not possible. So let's look at this graph and see if it has any interesting properties. What I want to focus on is this part right here. And does this look familiar? So you can think about moving this around and redrawing it. If you redraw it, think about moving this vertex, pulling it out this way. And what will it look like? It will look like this. So what is this? This is K4. It's the complete graph on 4 vertices where each vertex is adjacent to all of the others. Meaning we need 4 colors to color this part, which means that this graph does not have a 3 coloring. So that's our proof by finding this copy of K4 in the graph. It proves that it's not 3 colorable. No. And it's because we found a copy of the complete graph on 4 vertices in our graph. This means we need at least 4 colors to color G, since each of these vertices is adjacent to the others in this K4 section. All right, so I hope you enjoyed that second lecture, and I'll see you in the next one for more on graph theory.